Hey everyone, I am absolutely thrilled to guide you through this explainer today. We are tackling the mechanics of solids. Now, I know you're all staring down the barrel of that 60-mark end semester exam, and the pressure is definitely on. But don't worry, because today we're taking a highly structured, concept-to-application approach to the source material. Let's get focused and conquer this exam together.
Here's our roadmap for the session. We will start with fundamentals, stress and strain, then decode elastic constants. From there, we'll conquer beams, navigate principal stresses, and wrap up with exam strategy.
All right, let's jump right in. Section 1, Fundamentals, Stress and Strain.
First up is stress. Simply put, stress is the internal resistance a body puts up against an outside force. It's the force, P, divided by the cross-sectional area, A. And it really comes in two main flavors for axial loads: tensile stress, which is a pull that tries to stretch the material, and compressive stress, which is a push that tries to squish or decrease its length.
Now, right alongside stress, we have strain. Think of this as the physical deformation per unit length. You calculate it by taking the change in length and dividing it by the original length. So the crucial point here, and watch out because this is a classic trap question on exams, is that strain is completely unitless. It's literally just a ratio representing how much the material has stretched or compressed relative to its original size.
So how do they connect? Enter Hooke's law. This rule states that when a material is loaded within its elastic limit, the stress is directly proportional to the strain. I really want you to mentally highlight this, because this single principle is the bedrock for almost every problem you'll solve in this first section. It bridges that invisible force, stress, with the physical deformation, strain. Sigma equals P over A. This fundamental formula is your absolute starting point. Whether you're dealing with a simple, axially loaded bar or transitioning into complex composite materials, you are going to be writing this formula down constantly. Lock it into your memory right now.
Moving right along to Section 2, Decoding the Elastic Constants.
Okay, meet your cast of characters for the exam. You absolutely need to know these four constants inside and out. Number 1, Young's modulus, E, which links direct stress to linear strain. Number 2, bulk modulus, K. Number 3, shear modulus, which you'll sometimes see written as C, G, or N. And finally, Poisson ratio, the Greek letter mu, which relates lateral strain to linear strain.
Let's actually visualize the bulk modulus, K. Picture a perfect cube being subjected to three mutually perpendicular tensile stresses of equal intensity. Bulk modulus is the ratio of that direct stress to the volumetric strain. Basically, it's a measure of how well a material resists a change in its volume under uniform pressure.
And here is your master equation. E equals 9kc over the sum of C plus 3k. For your exam, you'll often be given two constants and asked to find the rest. This combined equation relates Young's, bulk, and shear moduli all together. If you memorize this, along with the individual relations like E equals 3k times 1 minus 2 mu, you're going to breeze right through the elastic constant numericals.
Next up, Section 3, Conquering Beams, SFD and BMD.
Let's start with the simplest case. Picture a cantilever beam with a concentrated point load sitting right at the free end. Notice the shape of the resulting diagrams. The shear force diagram is a simple rectangle, but look at the bending moment diagram. It's a linear, triangular curve. A point load creates a linear bending moment.
Now let's see how this builds when we change the load. We have the exact same cantilever, but with a uniformly distributed load, or UDL, spread entirely across the top. The shear force diagram is now a triangle, but the bending moment diagram has transformed into a parabolic curve. The mathematical degree of the curve literally stepped up by 1.
Finally, check out the progression when we introduce a uniformly varying load, or UVL, which is often shaped like a triangle itself. The shear force diagram becomes parabolic, and the bending moment diagram becomes an even more complex cubic curve. For the exam, remembering this progression, linear to parabolic to cubic, is a massive shortcut for checking if your drawn diagrams are actually correct.
All right, moving to Section 4, Navigating Principal Stresses.
This entire concept hinges on one huge question. What happens to stress on an inclined plane? Up until now, we've analyzed forces acting neatly on standard x and y axes. But in real-world structural failures, materials don't just break along perfect horizontal or vertical lines. We absolutely have to know what those forces are doing at an angle.
To map out that chaos, we look at an element subjected to combined biaxial stress, so pulling in both the x and y directions, plus shear stress sliding along the edges. When we cut a plane at an angle, theta, we have to resolve all of those forces into a new normal tensile component and a new tangential shear component.
Which brings us to the big one, the master formula for principal stresses. Sigma 1 and 2 equals the average of the normal stresses plus or minus the square root of the difference divided by 2 squared plus the shear stress squared. You 100% need this committed to memory for Part B of the exam. This is how you find the absolute maximum and minimum stresses the material will ever experience, which specifically occur on planes where the shear stress is 0.
Let's bring it all home. Section 5, Exam Strategy and Wrap-Up.
Let's break down how this end semester examination layout actually works. You have 2.5 hours for 60 marks. Part A requires you to answer all 8 questions at 3 marks each. These are going to be quick definitions like define Hooke's law or simple one-step calculations. Part B is where the heavy lifting happens. You choose 4 questions, each worth 9 marks. This is where your long SFD and BMD drawings or your complex principal stress calculations using that massive formula we just saw are going to live. So balance your time accordingly. Do not spend 15 minutes on a 3-mark question.
Which leaves us with this final thought. As you prep for this exam, remember why you're learning all of this. Sure, you can calculate the internal forces on paper today, but how are you going to use these principles to design the robust, safe structures of tomorrow? Mastering the mechanics of solids isn't just about passing a 60-mark test, it's about building the foundation for your entire engineering career. Keep studying smart, use this explainer as your blueprint, and go crush that exam.